Today, we're going to dive into some really fascinating work that tackles a notoriously difficult problem. How do you accurately map 5G signals inside a complex building when all you have is data from a drone flying outside? The answer, as we'll see, lies in a powerful technique called dynamic graph attention networks.
So take a look at this. This image really gets to the heart of the problem we're tackling. You've got a UAV. It's collecting signal data, but only from the exterior of a massive building. The fundamental question, the one this whole paper is about, is can we take those sparse external measurements and use them to accurately reconstruct the entire 3D signal landscape inside? That is the core challenge.
Okay, so here's how we'll break this down. First, we'll formally define what we mean by the indoor inversion problem. Then we'll walk through the three key methodological stages: how the model builds its understanding of the space, how information travels through that model, and finally, how it spits out its predictions. And to wrap it all up, we'll look at the hard numbers and visualizations that prove this whole thing actually works.
First things first, let's really nail down the problem we're trying to solve. The paper calls it the indoor inversion problem, and that's a perfect name for it. It's all about bridging that huge gap between what we can easily measure on the outside and what we desperately need to know on the inside. So what is this inversion problem? Well, in formal terms, it's the challenge of inferring a latent, unobserved internal state, which for us is the detailed 5G coverage map inside a building using nothing but a limited set of data points collected from the outside. You can see why this is so hard. It's a classic case of trying to understand the whole picture from just a few scattered puzzle pieces. Now, this is where things get really interesting, because it shows us exactly why the old ways just don't cut it. Your baseline models, things like k-nearest neighbors, or even some deep neural networks, they all share a fundamental flaw. They rely on Euclidean distance. They make the simple assumption that if 2 points are physically close, their signal strength should be similar. But think about a real building. A concrete wall or an elevator shaft completely breaks that assumption. Our proposed approach, TAGAT, just throws that idea out the window. Instead, it learns a graph based on feature affinity, figuring out the hidden paths that radio signals actually take.
So the big question is, how does it do that? Well, it all starts with the first part of our methodology: dynamic graph construction. This is where the model learns to see the world not as a simple grid of coordinates, but as a complex network of signal relationships. And here's the first major piece of the puzzle: the latent topology inference module. Think of this as the model's brain for understanding the real structure of the building. It takes in all the features for every single point inside the building. RF data from the drone, even architectural info like how many walls are in the way. And its one and only job is to build a graph. But crucially, it's a graph where a connection between 2 points means they have a strong signal correlation, even if they're on opposite sides of the building.
So let's get into the math that makes this possible. It's a three-step process. First, as you see in equation 1, we take our input features for each node and project them into a new learned embedding space. Simple enough. Second, equation 2 computes a pairwise affinity score. This is basically a scaled dot product that tells us how similar any two nodes are in that new feature space. But the third step is the most important. It enforces sparsity. We don't want a messy, fully connected graph, so for each node, we only keep the top k strongest connections. This filters out all the noise and weak correlations, leaving us with a clean, meaningful graph that represents the true signal pathways.
Okay, so we've built this incredibly smart graph. Now what? How does information actually move across it? That brings us to the second stage of the methodology, which is all about residual feature propagation. The engine that drives this is what we call the topology-aware feature encoder. At its core, it's a stack of graph attention network layers, or GAT layers. The whole purpose of this encoder is to let each node iteratively pull in information from its neighbors across that dynamic graph we just built. This process effectively diffuses the signal context throughout the entire building, allowing a point deep in the core of the structure to be influenced by a point right next to a window, but only by following the real paths we inferred. And this equation right here is the magic behind each layer's update. Now, I want you to focus on that last term, the plus LT minus 1. This is what we call a residual connection, and it is absolutely critical. See, with deep graph networks, you run into this problem called oversmoothing, where after a bunch of layers, all your nodes start to look the same. This residual link acts like a highway, a shortcut, that makes sure the original fine-grained information from the earlier layers is never lost. It's essential for maintaining signal fidelity. All right, quick recap. We've built the graph, we've passed information across it.
The last step is to actually turn all that rich, contextualized feature data into our final predictions. This is where the third module comes in, bifurcated signal decoding.
And the fundamental insight here is that not all signals are created equal. You just can't treat them the same way because the physics that govern them are totally different. RSSI, your signal strength, is mostly about large-scale things like path loss and shadowing. It changes slowly. But CQI, your link quality, is super sensitive to small-scale, high-frequency stuff like interference. So trying to predict both with a single one-size-fits-all decoder is just, well, it's suboptimal. The model's architecture has to respect the physics.
So, what does the model do? It gets smart. It splits into two specialized heads. On the left, you've got the RSSI branch. It's simpler, designed to capture those broad, slow-moving trends in signal strength. But on the right, for CQI, the architecture is way more complex. It needs a much more sophisticated attention mechanism to zero in on those tiny variations that actually define signal quality.
Let's zoom in on the RSSI branch. It uses a pretty straightforward mechanism called a scalar attention gate. This equation calculates a single value, lambda, for each node, somewhere between 0 and 1. You can think of this lambda as a reliability score that the model learns. It acts as a gate, telling the model exactly how much to trust the information from that specific node before it makes its final RSSI prediction.
Now, the CQI branch, that's a different story. It needs something way more sophisticated, what we call a dual attention mechanism. As you can see from the equations, it's actually calculating two separate attention maps. One is channel-wise attention, which figures out which features in our data are most important. The other is spatial-wise attention, which determines which neighboring nodes are most important. It's this dual focus that gives it the power to model the much trickier, more volatile nature of link quality.
So just to put this in more practical terms, if you were coding this up in, say, PyTorch, here's how you'd think about it. You'd have one shared GAT encoder that processes the graph. Then its output would get fed into two completely separate, parallel torch.nn.module classes. The RSSI head would be simple, implementing that scalar gate probably with a sigmoid activation. But the CQI head would be more complex, using parallel linear layers to compute those two distinct attention vectors before they're finally used for the prediction.
Okay, so that's all the theory, that's the architecture. It sounds good on paper, right? But the real question is, does it actually work? Let's get to the empirical validation and see the results.
And the results, well, they speak for themselves. The numbers here are just staggering. I mean, look at this. Compared to the previous state of the art, we're seeing a 76% reduction in error for RSSI and an absolutely massive 89% reduction for CQI. And those R-squared scores, both over 0.99. That's a nearly perfect correlation between what the model predicts and the actual ground truth. This isn't just an incremental improvement, it's a total game changer.
And if you're a visual person, these plots tell the whole story. On the left, you've got the baseline model's predictions. See how messy and scattered that is? The points are all over the place, far from that ideal diagonal line. Now look at our framework on the right. It's a clean, tight, beautiful line. This is what an R-squared score of 0.99 looks like. The fidelity is just on another level.
So after all that math and all that architecture, what do we actually get? We get this. A complete high-resolution 3D heat map of the predicted indoor RSSI. We can now see, floor by floor, room by room, exactly where the signal is strong and where it's weak. And remember, all of this was generated from that one drone flight on the outside.
And then we have the corresponding map for CQI. And you know, for a network engineer, this might be even more important. This lets you pinpoint with surgical precision the exact zones that have poor link quality, the places where calls drop or data slows to a crawl. It tells you exactly where you need to go to fix the network.
So let's just boil this all down to the key takeaways. First and most importantly, you have to move beyond Euclidean distance. Learning the dynamic topology is the only way to handle complex indoor spaces. Second, residual connections are not optional. They are vital for preserving information in deep graph networks. Third, let the physics guide your architecture. Building task-specific decoders for RSSI and CQI gives you massively superior performance. And finally, when you put it all together, you get a model with incredible fidelity, capable of creating these beautiful and, more importantly, accurate 3D maps.
And this, of course, leaves us with that exciting question. Where do we go from here? This framework proved itself on 5G, but could the same core principles work for the much trickier, higher frequency MM wave spectrum? Or, and this is a really cool thought, could you close the loop?
Could the drone use its own real-time predictions to plan its next move, actively hunting for areas of uncertainty to make its own map better? That's the future of this research.